So just to clarify again with our sampling distribution of the sample mean, okay, that's what this is saying right here. Sampling distribution of the sample mean because it's an X bar, okay? So if you have your whole population, you take a sample of just a few of those people that are in your population. The mean from your sample will equal the mean from your population. That's what this is saying. And the standard deviation from your samples will equal the standard deviation of the population divided by the square root of the sample size. Okay? Now, a couple of notes on that. One is that if the original population is normally distributed, then your samples will be normally distributed, okay, regardless of the sample size. Okay? Now, if your original population is not normally distributed, let's say it's right skewed, okay, well then, remember how we said the tall skinny graph, okay, so that the tall skinny one came from a normal population. The population was normal, the sampling distribution of the sample means was also normal. Your samples graph was normal. But when your population is not normal, maybe it's skewed, your sample distribution of your means, your smaller groups, will still be normal, okay, if your sample size is large enough. So as n increases, as your sample size gets bigger and bigger and bigger, your sampling distribution, your group of samples, will become normal even if your original population was not. That is a big deal, okay? And that is something called the central limit theorem. The central limit theorem says no matter what shape your original population was, your SDSM, your little sample graph, will become normal as your sample size gets larger, okay? And our magic number is 30. If our sample size is 30 or larger, that's enough for us to say, hey, you know what? My little sample group is going to be normal, okay? All right, so we're about to work a couple of problems here. We're still using normal CDF, okay? Lower bound, upper bound, mean, and standard deviation, okay? So if they say, hey, what's the probability that the one person you pick is over 5'6", or what's the probability that the one person you pick is shorter than 5'2", or whatever, you are still going to use normal CDF just like we've been doing, okay? Where it becomes different is if you have a sample or a group of people. Instead of just picking one person, you say, hey, what's the probability that when I pick 8 people, the mean height of those 8 people is over 5'6"? So you're going to have a group. Your lower bound will be the same, your upper bound will be the same, your mean will be the same. What will be different is the standard deviation. If they want you to find the probability that the average for a group is over a certain number or under a certain number, you're going to take whatever the original standard deviation was and divide by square root of your sample size. Okay? All right. IQ scores for adults is normally distributed. Okay? Since they tell us it's normally distributed, we know, hey, we can use normal CDF. The mean is 100, standard deviation is 15. Okay? All right, so I know that I can draw my curve here. I know there's a 100 in the middle. I know we can count by 15s. So 115, 130, 145. I can count by 15 this way. 85, 70, 55. Okay? All right. If one adult is chosen, we randomly go grab one random person. Okay? What is the probability that their IQ score is greater than 110? Okay, well, 110, I'm going to estimate, is going to be about right here. So they want the probability that the IQ is greater than 110. Okay? Okay, we picked one person. That means we're doing our normal CDF, just like we did in Chapter 7. Our lower bound is 110. Our upper bound is infinity. I don't have an infinity button, so I put 1E99. The mean was 100, standard deviation was 15, and that's what I'm going to type in my calculator. Okay? So I go to second vars. I pick normal CDF. Lower end is 110. 1E99 is my upper number. 100, standard deviation is 15. Remember, if you're using an 83, it won't prompt you for these things. You just have to know the order it wants and put the commas. Okay? And it says 0.25 2, and I'm going to round the fourth decimal up to a 5 because the last number is 5 or higher. Now, remember, we found area. We wanted the probability that the random person we picked was in this region. So that's an area. So we round to 4 decimals. There is about a 25% chance that if I grab a random person, their IQ will be over 110. Now, compare that to Part B. In Part B, we're not picking 1 adult, we're picking 9. 9 adults are chosen. Find the probability that their mean IQ is greater than 110. So notice the difference between these two questions. In Part A, we were picking 1 person. In Part B, we're picking 9 people, and we want to know the probability that the mean IQ of those 9 people is greater than 110. Okay, so it's the same picture, but it really should be tall and skinny. So it's the same basic shape. It's still a normal distribution, but it's going to be a little bit taller and skinnier. 100 is still in the middle, and we're still counting by 15s. Okay? But it's taller and skinnier because if you pick 9 people, you're probably not going to get all 9 people from way out here. You're probably not going to get all 9 people from way down here. The 9 people you pick are probably going to be kind of scattered random throughout it. So the average of those 9 people is probably going to be real close to the middle here. Okay? But they're still asking us for the probability that the average IQ is greater than 110. 110 is still right here. We still want to know the probability that the average or the mean of those 9 people is above 110. So we're still finding the probability that IQ is greater than 110. We're still going to normal CDF. We're still having a lower bound of 110 and an upper bound of 1E99. Our mean is still 100. We still expect that if out of our 9 people, the average to be very close to 100. It's our standard deviation that has changed. The standard deviation is going to be smaller than 15. As the sample size increases, that standard deviation is going to get smaller, okay? And it's going to get very close to 15 divided by square root of 9, okay? Because remember they told us that when you have a group, your standard deviation is your old standard deviation divided by square root of the sample size. We had 9 people in our sample, so 15 divided by square root of 9 is going to be what we put in for our standard deviation there. All right, so second vars, normal CDF, 110, 1E99, 100, standard deviation 15 divided by square root of 9. And notice in my standard deviation spot it says 15 divided by square root of 9. Okay, what did I get? The answer is 0.0228 because that fifth decimal is 5 or higher, so it rounds up. Now notice what happened. The probability that the average IQ or mean IQ from my sample is quite a bit smaller than the probability of my just one random person being over 110. Went from 25% to about 2%. And the reason for that is because that graph of our sample got tall and skinny. The mean is still at 100, okay? The mean of the population still equals the mean of our sample group. It's still equal to 100, but the standard deviation is smaller because you're probably not going to pick all 9 really smart people or all 9 lower people. You're probably going to have a mixture. So the mean will be very close to the population mean of 100, but there's going to be less variety. Okay? So the original population mean was 15. The standard deviation of our original population was 15. The standard deviation of our samples is going to be 15 over square root of 9. By the way, this symbol, sigma, is our standard deviation. And that works when you're dealing with a population. When our standard deviation is talking about sample means, okay, when we use this symbol, we no longer call it standard deviation. We call it the standard error of the mean. So standard deviation, but when we put the little X bar next to it, we call it standard error of the mean. I think there's a homework question that asks you that. Okay, so just know that when it's standard deviation of your little sample groups, we call it standard error of the mean. Okay. Also, as sample size increases, okay, the sample size increases, n gets larger and larger and larger, your standard error of the mean decreases. It's going to get smaller, and that's why that graph gets tall and skinny. Okay? Remember, our magic number is 30. When they tell you that that sample size is 30, you have enough to know that your skinny graph, your sampling distribution of the mean, will be tall and skinny and will be normal shaped. Okay? So notice here, on this last example with IQs, our sample size was only 9. 9 is not above 30. 9 is not enough for us to go, oh yeah, it's normal, do normal CDF. The only reason we could use normal CDF is because they told us that the original population was normal. If they had not told us the original population was normal, we would not have been able to use normal CDF on these two problems. Okay? Okay. Example here. For women age 18 to 24, the systolic blood pressures are normally distributed. That means we can use normal CDF with a mean of 114.8. 114.8 is in the middle, and the standard deviation is 13.1. We could count by 13.1s. Part A, if you select one woman, find the probability that her systolic blood pressure is greater than 120. So what's the chance that she's out here above 120? Okay, well, they told us it was normal, so normal CDF, above 120. So 120 to infinity. We don't have an infinity button, so we use 1E99. The mean was 114.8, and the standard deviation is 13.1. We're going to type that in our calculator. And we get 0.3457. There's about a 35% chance that the one woman we pick will have a blood pressure above the 120 number. Okay. Part B. If you select 36 women, find the probability that their mean systolic blood pressure is greater than 120. Okay. Now notice, 36, that's a group. We're finding a sample of women. I'm going to make this shape still normally distributed, but it's going to be a little bit skinnier. 114.8 is still in the middle, but notice my standard deviation would be a little bit smaller. In fact, it won't be a standard deviation. We'll call it the standard error of the mean. Okay? Now notice, even if the original population had not been normal, maybe the original population was skewed left or skewed right, since our sample size is over 30, we're guaranteed that it's going to be a normal distribution for our sampling distribution. So I can still use normal CDF, 120 to infinity. My mean is still 114.8, but I will not be using 13.1 for the standard deviation. In fact, this does not have a standard deviation. It has a standard error of the mean. So 13.1 over square root of 36. Okay, remember that's called standard error of the mean. So I'm just changing that standard deviation number to 13.1 divided by square root of 36. And we get 0.0086. Notice how much smaller that is. there's less than 1% chance that the average of our 36 women will be above 120. Okay? Because that graph, it's a much smaller area under here than under the whole thing, like we had up here. Smaller area here than under the whole thing. Because as our sample size increases, that graph gets taller, skinny. Okay? Hopefully that helps, but that will get you through the 8.1 material.